Hey everyone, how's it going? Terry Brown, Mechanical Engineering here with another engineering mechanics video. In this video, I'm going to do a lecture on the moment of a force. So let's have a look at it. Right, so in this lecture, the objectives are for us to understand and define what a moment is, to determine the moment of a force in just 2D cases, to understand and apply Varignon's theorem, also known as the principle of moments, and to look at an example where we determine the resultant moment of a number of forces in a 2D example. So firstly, some examples of what may happen if moments aren't considered properly. Moment of a force is the tendency to cause rotation of a body about some axis, some distance from the line of action of the force. So we can see here this blue thing with a force applied to it, and we've specified some rotation axis, and that's going to cause a rotation about that axis. So let's say there was a pin through here, and we could just rotate something around on that. So we have a force on its line of action, so it's important to understand the line of action of a force. We should know that the force, or a force, is a sliding vector, so we can move it anywhere along its line of action. Yeah, so that continuous straight line on which a force vector lies is called its line of action, and the moment is calculated by r times f, or r cross f. So this is the vector formulation of the moment equation, which we'll look at in more detail in a later video. We're going to simplify it in this video to just 2D cases. So if we redraw our shape here with the force applied to it, we have the sense of rotation. See that will tend to rotate this thing, if we're looking down from the top, around anti-clockwise, and we can have a symbol showing the rotation and the moment shown as a vector. So F is the force vector, and this thing here, R, is called the position vector, which we'll look at in more detail later. So the moment is a vector with magnitude and direction. Okay, so this darker or thicker dotted line here with an arrow, that shows the vector for the moment. And if we use the right-hand rule, so hopefully you've seen the right-hand rule before, if fingers curl in the direction of the rotation, then your thumb on your right hand will point in the direction of the vector. Okay, so that's just what I've shown here in this little picture. All right, so for 2D problems, we can simplify this and say that the magnitude of the moment is simply force times distance, where now the distance d is the perpendicular distance from the line of action of the force to the axis of rotation. So if we look down here at the bottom right hand corner of my slide, we're now looking at a 2D view, looking down the z axis or down the moment axis, and we've got this force here along its line of action. So when we work out the moment of that force, we need to know the point about which we're calculating the moment, and really it's the point where the axis passes through. Right, so in this 2D problem, the axis is in and out of the page. So we want the distance from the point where we're taking moments about perpendicular to the line of action of the force. Okay, so that distance there is our distance d. Right, it's not the distance from O to the head of the force arrow or the end. Right, so it's not the point of application of the force that's important. It's the line of action of the force. That's the important. And if the force is in the XY plane, then the moment vector is in the Z direction, and I've shown this up here. So if our force is in this horizontal plane here, the force is in the X direction, or in the XY plane, whether it's in the X direction or the Y direction, doesn't matter, as long as it's in the XY plane, then the moment vector is in the Z direction, normal to that plane. And using the right-hand rule, if the Z axis is directed out of the page, so if we're looking down here, the Z axis will be directed out of the page, and counterclockwise moment will be positive. Okay, and because it's, if we look up here, force times distance, force is in newtons, distance is in meters, then the SI units for moment are newton meters. You should really, when you write newton meters, put a dot between them to be strictly correct. So here we've got units that are compound units, right? So we should have a dot between the N for newtons and the M for meters. In general, in your 2D problems, the sense of a moment could be clockwise or anti-clockwise, depending on the tendency for rotation. So if we had this force directed in the opposite sense, so directed towards the left, then the moment would be clockwise about point O. In 2D problems, it doesn't matter if you assume clockwise or counterclockwise or anti-clockwise as positive, as long as it's clearly stated and you're consistent. And you'll see in other YouTube videos and so on that people assume clockwise as positive. However, if the force is in the XY plane and the Z-axis is directed out of the page, a counterclockwise moment is the strictly correct positive direction. If we look up here, if we have X and Y coordinates like this, where the Y coordinate is 90 degrees anti-clockwise from the X-axis, then to be strictly correct, anti-clockwise is positive, right? Because of the right-hand rule that I just showed you on the previous slide. In all cases, use a symbol, something like this, an arc with an arrowhead and a plus to indicate the direction or sense that you've assumed is positive for your calculations. When you're writing a moment and doing the calculations for calculating a moment, you should always have a subscript to indicate the point about which you've calculated that moment. Okay, so we can calculate the moment of a force about any point or axis, and without that subscript, the reader can't determine which axis the moment has been calculated about. Okay, so you can look at the working out and try and guess, but if a reader has to guess what you've done, then you haven't communicated clearly enough. Right? It should be clear in your working out and in your solution where the moment has been calculated. Yeah, so the subscript O in MO means that the moment is about an axis perpendicular to the 2D plane that passes through the point O. And of course, the orientation of the force as well as its magnitude must be taken into account when calculating the moment. And we'll see that more clearly in the following slides. If there are multiple forces acting, so here we've got 3 forces acting. If we have multiple forces, then we can just simply add the moment effect of each of those forces to get the total moment effect or the resultant moment. Okay, and again here I've clearly indicated everything that the reader needs to know in interpreting what's going on in your solution. Okay, so here I've indicated anti-clockwise as positive or counterclockwise as positive, whereas the moment resultant calculated it's about point O, and so on. If we take anti-clockwise as positive and we look at all of these 3 forces and their moment effects, work out their perpendicular distances, we have 2 positive moments from F1 and F3 and a negative moment from F2. I'm often asked, well, what's the difference between moment and torque? Essentially nothing, right? We calculate them in the same way, but there are some circumstances where we tend to refer to the turning effect of a force as a moment, and some circumstances or situations where we refer to it as a torque. So if the force causes the body to which it is applied to bend and rotate about a transverse axis, then it's usually called a moment. So for example, this lug wrench here, so while the nut is still tight, right? So in that situation, when you apply this force here, you'll tend to get some bending happening. So let me just get my pen and I'll just see if I can draw this. Not very good at drawing with my mouse, but anyway, so here, this will kind of tend to bend down like this, and it will tend to bend this like a beam. Then when it becomes loose, it starts to rotate around this transverse axis. Okay, so generally we refer to that as a moment. If the force causes the body to twist or rotate about its axis, so if we look at this short little bit of the lug wrench here, that will be twisting, or if we're rotating the nut about its longitudinal axis. Okay, so in this case, the x-axis is now a longitudinal axis, then we generally refer to that as a torque. Force can also be, the moment can also be thought of as the leverage of the force, but in any case, the torque is calculated in exactly the same way. Important to understand the difference between line of action of the force and the point of application of the force. So in the two examples below here, the force has the same point of application, but the lines of action are different. Okay. And over on the left here, if we wanted to work out the turning effect of this force or its moment about point O, we would need to work out this perpendicular distance from the line of action of the force to point O here, right? And that would be this distance here, D. Over here, our force F, its line of action now passes through point O. So its perpendicular distance will be 0, as I've indicated here. Okay, so this force has a 0 moment about this point here. Right, so look at me across to the side here. Right, with the first one, we get turning moment like that. Tends to rotate the structure counterclockwise. Put that back there. Pull on here. And if I do move that over, like hit over here now, and I pull on that, nothing happens. Right? Still, if I go back the other way, you can still see it's loose. I haven't tightened it up. So if I now pull it like this, nothing happens. No turning effect. A common error made by students is to mistakenly use the distance from the point of application of the force to point O. So they might use this distance from here to here. So here you will calculate a value if you use that distance between the point of application and point 0. You'll get a value, but it will be the wrong value. Right? You'll get the wrong moment. And here, again, students might be tempted to use this distance and do F times this distance here. Again, they'll get the same value as they got over here, right? But it would again be incorrect because, as we've just seen, the moment effect of this force about point O is 0. All right, so let's have a quick look at a quick example. Over here, we've got some gears connected together. We've got a torque applied to this gear over here, and then that's transmitted through these connecting gears here to another shaft. Right, this is not going to be rigidly attached to ground at each end here. You know, that'd be a bit silly. So this is just representing that it's attached to some other piece of machinery where there's some loads being applied or transmitted. But anyway, so what we're going to do is to look at just this gear D here and to work out the moment effect of the force that's generated between the two gears, right? Or the torque that's applied to this gear. So let's just say we're looking at the gear, and at this connection point between gear C and gear D, we've got those gears in contact, and there's a force being transmitted between them. Right? So if I drew gear C over here, we'd have equal and opposite force acting down on a tooth of gear C. In actual gear systems, you have a pressure angle, and the total force will be at some angle. Okay, so in this case, in most gears these days, you have a pressure angle of 20 degrees. You may see some gears with a pressure angle of 14 degrees. But yeah, so we have this force that acts at 20 degrees to the tangent to the gear. All right, so that's a bit of background and context. Let's get to the point and work out the moment effect of this force. Right, so far what we need to do is to work out, given this force and its line of action, work out the perpendicular distance from point O to the line of action of that force. Okay, so just need to do a little bit of trigonometry. So if we extend our line of action here, draw a line perpendicular to that line of action, we know the radius of the gear. We've got that. We've got the contact angle, or the pressure angle rather, for the gear. And from trigonometry, hopefully you can see that this angle in here will also be 20 degrees. So we can simply work out the length of this side of the triangle from Pythagoras and right angle triangles to get 150 cos 20 gives us 141 millimeters. So we can now just put that into our calculator and we get 7.05 Newton meters. So just note here that I've converted from millimeters into meters in this part of the calculation, and I've shown clearly that in my by having units at the end of my calculation here. Some of you may already know about this and been thinking, well, why didn't you do it a different way to what I've just done? And that is to use Varignon's theorem, or what it's also known as the principle of moments. So Varignon's theorem states that the moment effect of a force is equal to the sum of the moment effects of the components of that force. Right, so in this example here, we've got the post with this lug on the end here. We've got a force applied. If we're just using force times perpendicular distance, we would have to extend our line of action here and find this little perpendicular distance down here. Right? So usually that's a little bit more difficult than breaking this force up into its components and finding the moments of each of those component forces. Just note here in the equation that we've got a negative sign, because in this problem we'll end up with a clockwise rotation. Okay, so as I said, it's often easier to work this out by using Varignon's theorem, and we do that by resolving or breaking this force up into its components along directions that are convenient for us to do the calculations of the moment. So in this problem, right, typically you would know from the design of this structure what the height of this is, how far this application point is away from the base. So usually these distances would be known. So if we resolve this force into components in those directions, then we can simply make use of the sum of the moment effects of each of those components to work out the total moment. Okay, so we can just do Fx times its perpendicular distance. So again, if we extend our line of action out here, perpendicular distance here is this one dy, and that's tending to cause a clockwise rotation. Right, if you're not sure, just get your pen, hold it at the point where you're taking moments about, push where the moment, or push where the force is acting, change hands, right, and see which way it goes. So that's a clockwise moment. So that one's negative. You can see that in here. And then for Fy, it's a bit harder to do that with a pen, but you just need to remember that it's the line of action of the force, which is down here. Perpendicular distance is now horizontal. So now if we just push Fy, let me do this the right way, over here, push like that, and it goes anti-clockwise. So that tells you that this one's positive. Okay, assuming that you've using x to the right, y positive upwards, and using the strictly correct assumption for positive moments as anti-clockwise. Okay, so note the different signs on the terms that I've just talked about. All right, so let's go back to our problem at the moment on the gear about point O. So now, because we already know this radius, if we resolve the force F into components tangential and normal to the circumference or the pitch circle of the gear, right? So we now have this. So we resolved our force into its components tangential to the pitch circle and normal to the pitch circle. Just note that I haven't drawn my components. Let's get my pen. Right? I haven't drawn, for example, my component for the y direction out here, okay, which many of you are probably in the habit of doing and would have seen in online physics videos, for example, on calculating components of a force, that they'll draw them like this. Or they might have drawn Fx down here like this. Okay. Now, I recommend that you don't draw your components like that. Don't do that. The reason is, let me just go to our calculations here. So when we're calculating the moments about point O, right, we look at the force and its perpendicular distance. So here we've got force in the y direction, perpendicular distance is just r, so we've got that. And then when we look at Fx, we say its line of action is through point O. So there's no perpendicular distance between point O and its line of action. Okay, so there's zero moment here. If you draw Fx down here, it looks like its line of action is at some distance from point O, when it isn't. Okay, so you might say, well, I can think through that in when I do the problems, I know that it's actually here. Well, yeah, great, but why not draw it where it's supposed to be? All right, so putting in our values now, and we get the same answer that we got before. Okay, so that's Varignon's theorem, or the principle of moments. All right, so let's do another quick example. So here we've got my little structural component, post with this little triangular lug sticking out here. Now we've got a force and some value and an angle, and we've also got the weight of the lug acting at 200 millimeters from point A, and its weight is 100 newtons. So determine the resultant moment about point A. So always think about the plan for your solution. So we're going to resolve the force F into components along horizontal and vertical X and Y axes, and then we're going to determine the moment using scalar analysis. All right, so firstly, resolve the force into components along horizontal and vertical axes. So let's define what they are. So here's X and Y, and we're taking anti-clockwise as positive. Put the components on our diagram. So here we've got Fx. So again, don't draw it out up here, and don't draw Fy out here. Show them in their proper lines of action. And then from Pythagoras, right angle triangle, hopefully you know from high school maths how to work out the lengths of the adjacent and opposite sides. So here, this side Fx is adjacent to this angle, so this one will be 400 cos 30, and the opposite side here will be sine 30, so Fy is 400 sine 30 newtons. So now we can determine MA using our scalar analysis and the algebraic sum of the moments of each force. So we've got, let's work our way through this. So we've got 400 cos 30, so this is Fx. Perpendicular distance is 900 or 0.9 meters, and it's tending to rotate about point A in a clockwise direction. Okay, I went through that before, so I won't do that again now. Then we've got Fy is acting upwards here, so tending to cause an anti-clockwise rotation about point A. So 400 sine 30 times 0.5, which is its perpendicular distance. And then we've got 100 newtons times 0.2, tending to cause a clockwise rotation about point A. So that one's negative, and we put all that into our calculators, and we get minus 232 Newton meters. Right, so that indicates that the resultant moment is clockwise. So let's have a quick think about our answers. Is that going to be correct? So when you do your solutions on paper, whether that's electronic paper or physical paper made out of trees, when you draw your diagrams, try and draw them reasonably accurately. so that you can just look at your solution and get a feel for whether it's right or not. Okay, so if I extend my line of action of this down here, right, my perpendicular distance is going to be something like this. Right, so that distance there, 0.4, 0.5, something like that. So 400 times 0.4, let's say 0.5 to make it easy. So that's about 200 Newton meters. And it's tending to cause a clockwise rotation about 0.8, so negative, right? And then, so that's about 200 Newton meters. And then we've got here 100 times 0.2, so that's about 20 Newton meters, also tending to cause, if we continue our line of action down here, here's our perpendicular distance, right, 0.2, tending to cause a clockwise rotation again. So 200 plus 20, or thereabouts, is about 220. So we can see that our answer is roughly in the right ballpark, right? Just from having a look at the problem and getting a feel for what the answer should be. Right, so if you do that, so let's say we had have put a minus sign here instead of a plus sign, we would have got a much bigger answer here, right? And so that would have told us, hang on, I think we've probably done something wrong. Or if we had put a plus sign out the front here, if instead of a minus we had a plus, we'd get a positive result. And so that we would see from having done our thought experiment here, just thinking through the analysis, getting a ballpark answer, we would have seen that that would also be wrong. So a bit of a recap quiz to finish this off. All right, so stop the video and come up with your answer. All right, so hopefully you did that and you got an answer of 20 newtons. Right, so we've got here 30 minus 2 times 5 is 20. Okay, and it will be anti-clockwise. Right, so here's another one. Stop the video. Okay, so hopefully you stopped the video and you've got an answer. So let's see what my answer is. Okay, 30 Newton meters. So again, here it's not 100 times 0.5. If you've got 50 as an answer, right, we need to know we need to use the perpendicular distance from the line of action of the force. Right, so 100 times 0.3. Right, we've got another one here. Stop the video. Okay, hopefully you stopped the video and you're back, having come up with your own answer. So let's see what we got here. So 75 Newton meters clockwise. So again, perpendicular distance is 0.3. 0.3 times 250 is 75. All right, let's have a go at this one. Stop the video. Okay, hopefully you're back. Hopefully you've done a calculation. Please don't just wait for me to give you the answers. It's really important that you actually have a go at these. All right, so let's have a look at what my answer is. So none of these other answers are correct. So if you chose B, what value did you get for your moment? If you got a value other than 0, then you got an incorrect answer also. Okay, right? Because again, remembering that it's the line of action, perpendicular distance to the line of action of the force. Right? And this force here will pass through, its line of action will pass through point A. Here's another one. Okay, so have another quick go at this one. So this one is about understanding the difference between the direction of the force or the sense of the force and the sense of the moment caused by the force. All right, so in this one, we get MA is 30. So taking moments about point A, anti-clockwise is positive. So we've got 30 times 2 minus 1 here. So 30 times 1, 20 times 3, perpendicular distance going clockwise about point A, and then 10 times 4 going anti-clockwise, so positive. All right, so have another go at this one. stop the video. All right, so hopefully you're back and you've had a go at this one, and this time taking moments about point B this time. So we have 30 times 0.1. So this one hit 30 times 1 going clockwise about point B. All right, so here you can see this first term for the 30 Newton force. The sense of the force hasn't changed, but because we're looking at taking moments about a different point, the sign out the front has changed because the sense of the moment or the tendency for rotation has changed. So here, when we were taking moments about point A, this force tended to cause an anti-clockwise moment, so therefore positive, whereas taking moments about point B, this 30 Newton force causes a clockwise rotation about point B. Yeah. Okay, and then hopefully you can work through the others. So last one, looking now at point C, calculate the final number, and hopefully you get minus 70 Newton meters. So here we've got, right, so the 10 passes through point C, so no moment from that one. 20 times 1 anti-clockwise, so that's 20, and 30 times 3 will be 90 in the negative direction, so minus 90 plus 20 is minus 70 Newton meters. All right, so that's the end of this little video. That was quite a lot longer than I wanted it to be. But anyway, hopefully that covered everything that we need to know for 2D analysis of the moment of a force. In a following video, I'll look at using the vector equation and looking at vectors or moments in 3D. Right, bye for now. See you next time.